Thank you, Nalin. So yeah, today I'm going to talk about one-shot signatures, which are these amazing cryptographic primitives that I didn't even realize were possible to instantiate physically. And in my opinion, if we can get them to a practical stage, they will completely change the end game of blockchains. Yeah, I was mind blown, and I hope you'll be mind blown by this talk as well. So traditionally, when we think of a quantum in the context of blockchains, we think of it as an adversary, as something that's bad, that's going to break the cryptography and our lovely blockchains. So quantum breaks many signature schemes like BLS. It breaks many snarks like Planck, Halo, Nova. And it even breaks Bitcoin proof of work. But it turns out that with one-shot signatures, we can use quantum as a building block, not as a destructive technology. So this is really kind of a new paradigm in a way for us. And we have these different terms. We have quantum cryptography, where you're using quantum constructively, and you have post-quantum cryptography, like primitive like Fry, that are secure against quantum adversaries. And kind of somewhat counterintuitively, post-quantum cryptography will come before quantum cryptography. So my talk will be split into 3 parts. I'm going to focus on the basic definitions, the basic consequences of one-shot signatures, and then focus on the applications specific to blockchains. And then finally, I want to give you some of the intuition and some of the cryptographic details of how we can actually build one-shot signatures. And yeah, I just want to mention here that we should be having time for questions at the end, so plenty of time for questions. So in February 2020, a few years ago, this paper drops on ePrint, and no one notices it. There's very little citations, and I certainly did not know about it. But in my opinion, is this kind of this revolutionary paper that introduces a revolutionary concept, and it's been ignored largely for 3 years. And the idea of one-shot signing is that you have a signature scheme where the private key can only sign a single message, and then it destroys itself. So here we have the private key and the message that needs to be signed. We sign it, that's all good. But the very special thing is that the private key is meant to go poof. It's meant to destroy itself. And it turns out that the only way to do this is with quantum mechanics. So the color coding that I have here is that the purple corresponds to quantum stuff, and the blue corresponds to classical stuff. So the signature and the message is all normal bits and bytes, but the private key is like a quantum object, some sort of superposition. And one note here is that there's another concept called one-time signatures, which is different. A one-time signature is one where if you sign 2 messages, then you leak the private key, which is different here because here you physically can't sign 2 messages. Now, the reason why we can build these one-shot signatures is because of 2, at least in theory, is 2 quantum principles. The first one is the destructivity of measurements. So when you have a quantum superposition and you measure it, you kind of collapse it and destroy it. So the measurement process kind of collapses it to classical data, and then the quantum object destroys itself. And then there's the other principle, which is called no cloning, which is that when you have an unknown quantum superposition, you can't just clone it. And so these 2 things combined kind of give us hope that we can have a quantum private key that can only sign a single message. Now, one of the things that we want to do with one-shot signatures is kind of sign multiple messages over time, right? If you validate on Ethereum, you want to make multiple attestations. And so really what we want to be doing is building signature chains where we're chaining one-shot signature with the next one. And the way this works is that every one-shot signature will sign over the public key for the next one-shot signature. So basically, you take your private key for the current key pair, and then you're signing over the public key of the next key pair, and then you're basically giving the signing rights for the next signature implicitly to the next private key. So you create these chains. And the amazing thing about these signature chains is that they're unforkable. It's not possible to kind of go back. You can only go forward. It's kind of append only. And this is, of course, very reminiscent of blockchains, where we want like these very nice chains. We don't want them to fork. We don't want them to be trees. And in traditional blockchains, the way that we enforce the no forking is either through honesty assumptions or rationality assumptions and economics and incentives. But here, for the first time, we kind of have the opportunity to do it with pure cryptography. Now, another thing you can do with these signature chains is assign state to them. So imagine that you have a counter I that's assigned to every signature, and there's a validity condition which says that the counter must increment by 1 every time you sign. So there's this kind of this state transition function which describes how the state over the signature chain needs to evolve. And when you're verifying a signature, you really need to verify the whole chain before it and make sure that the state transition is correct. And if you snarkify all of this, well, you don't need to verify the whole chain. You just need to verify some sort of PCD, some sort of running proof that all the signatures have been correct so far, and all the state transitions have been correct so far. Now, I guess before I talk about this slide, let me go back to this slide here. Imagine that the counter I represents an epoch number in Ethereum. And imagine that the messages that you're signing are attestations. Now you've just constructed a scheme whereby you cannot double vote, right? You cannot vote on the same epoch twice, because by construction, the epoch numbers are increasing, and you just can't sign 2 messages with the same epoch number. And so what we can do is we can actually remove slashing conditions. We can remove the double vote slashing condition. And it turns out, with a little bit more work, we can remove the surround vote condition. So this is going to be our state transition function, where we have like 2 epoch numbers. We have the so-called source and the target. So we have previous source, previous target, current source, current target. And then if we have these 2 kind of validity conditions on the signature chains, then you can prove that slashing on Ethereum is impossible. So we can just remove the slashing conditions. And actually, as a side note, there's this project, Puffer, that has implemented these exact validity conditions within SGX. So the idea is that you have your keys within SGX, and then SGX kind of simulates one-shot signatures, if you will. But the downside, of course, is that you need to trust Intel and trusted hardware, but now you can do it with pure cryptography. Okay, now let's talk about applications of these one-shot signatures and signature chains. So one of the really amazing ones is perfect finality. So what we have today is economic finality. If there's 2 inconsistent finalized checkpoints, we have a guarantee that many validators, at least 1/3 of the validators, will get slashed. But with one-shot signatures, we can build blockchains which have perfect finality, which means that just by construction, you can't have 2 inconsistent finalized chains. And another kind of really cool thing is that we can reduce the threshold for finality. So today, in order to achieve finality, we need 2/3 of the validators to be online, and that can be reduced to 50%. And another thing that one-shot signatures solves is the weak subjectivity. Basically, we no longer have this in like the default case. So I call it ultra-weak subjectivity. And one of the consequences of that is that we can dequeue validators immediately when they activate or exit as validators. Because right now, as you probably know, on Ethereum, if a lot of validators want to come in at the same time and activate, it could take days, weeks, or even months because we have this activation queue and we have this churn limit, and the same thing on the exit. But with one-shot signatures and perfect finality, we don't have to worry about this, and we can immediately activate and exit all the validators that want to do so. Okay, let me just put this in a visual form for economic and perfect finality. So this is the status quo today. If there's two inconsistent chains that are finalized, so these are the two blue circles, both of which have 2/3 of the validators at least behind them, then it means that at least 1/3 of the validators have equivocated, and you can go slash them, and that's great because it's a disincentive to go equivocate. But with one-shot signatures, you can reduce the threshold to 50% because if there's two inconsistent chains, both of which has 50% plus one, then there's going to be at least one of them that kind of voted for both sides, but we know by the laws of physics and the laws of cryptography in this case that this is not possible. So that's kind of a security proof, I guess, that we have perfect finality. Now, another really interesting application is liquid staking. So today, when you have projects like Rocket Pool and Lido, in some very fundamental way, the liquid staking token is unsafe. And the reason is not, there's all sorts of risk, like contract risk and governance risk, but even more fundamentally, there's operator risk. You're trusting the operator to not slash the stake, and you're trusting the operator to not go offline and kind of get leaked. And it turns out that one-shot signatures kind of definitely solves the first one because it completely removes the slashing risk because we're removing these slashing conditions. But it also helps solve the second one, and that's due to this queuing thing that I mentioned. In really bad and extreme situations where many validators want to exit at the same time, it's possible that an operator can go offline, and the problem is that while they're in the exit queue, they leak. So they could leak for weeks and months. And so we have much safer liquid staking tokens in this paradigm. And I think once we have this, we'll be in a position where all the fear around Lido and delegation will basically just go away just through technology. Now, another aspect that's going to be improved with one-shot signatures is restaking. So restaking means that you can just opt in to arbitrary new slashing conditions. And there's basically 3 types of slashing conditions that you can opt into. There's basically safety and liveness, and within safety, there's deterministic safety and non-deterministic safety, or subjective safety. So deterministic safety is the same thing as no double voting. It's something where there's very clear rules and it's all deterministic. Subjective safety would be like an oracle, right? We all want to agree on what the price of ETH is in US dollars, and that's kind of a subjective safety thing. And then liveness is about disincentivizing going offline. And in a similar vein to the previous slide, we can solve deterministic safety. We don't need restaking for that. And liveness becomes much safer in this context because you can exit immediately, but subjective safety is not something that's solved. And so oracles kind of fundamentally seem to be extremely difficult to solve in a safe way relative to other things. Now, 2 final applications that I want to highlight before giving you some insight into how we actually build these one-shot signatures is quantum money and proof of location. So quantum money is this really cool thing, which is basically like cash, but digital cash. And it's another kind of way to think about it is that it's a bearer instrument that you can just give from one person to another, and it has similar properties to the Lightning Network. So you can send it over the internet, and you can send it instantly and privately, but it has all sorts of advantages over the Lightning Network. It doesn't have any routing problems. You don't need any fraud proof. You don't even need consensus. There's no routing issues and liquidity issues. It's just the perfect type of online cache in terms of its properties. And then there's this other application called proof of location, whereby you can try and locate someone geographically on the world just by using ping times and using like speed of light calculations. And the problem with proof of location today is that if you have a private key, you can copy it many, many times. And so you can kind of play games where it looks like you're in multiple places in the world, or you can try and obfuscate where you are. But with one-shot signatures, there's only one single copy of the private key, and so it's in one single place physically in the world. And so proof of location becomes much, much more tractable. Okay, final part for the cryptographers, I guess, for those curious as to how these things are built. So what I'm going to start with is just with one-bit signing, basically when the message is just one bit. But then we can easily generalize this to 256-bit messages or whatever we want. So I want you to imagine a hash function. Like for now, just imagine SHA-256, if that's easy, even though SHA-256 turns out is not completely suitable. But we start with a hash function. And it's in blue, so it's all classical so far. And what we're going to do is we're going to move to the quantum world, and we're going to take the uniform superposition of all input and output pairs of that hash function. So we're going to limit, for example, inputs to 512-bit strings, and the output is going to be a 256-bit string. And it turns out that in quantum computing, taking the uniform superposition of all possible strings is extremely easy. You basically just need to use these so-called Hadamard gates, and this is kind of table stakes. There's nothing fancy going on here. So basically what a uniform superposition means is that you have this object where once you observe it, you're going to get one input-output pair at random. Now, what we're going to do actually here is we're going to observe the so-called second register. So you can think of the superposition as kind of containing multiple qubits. It's going to contain 512 plus 256 logical qubits. And we're going to observe the last 256. And that's basically going to collapse the right-hand side of the pairs to a specific image of the hash function. And we're going to call this image Y. So this is going to be the public key for your signature scheme. And then what you're going to be left with is you're going to collapse so you've collapsed the right-hand side to a single public key. And what you're going to be left with is the uniform superposition of all the pre-images for this image, right? So if it turns out the image is like 0x, AC152, then the private key is going to be the uniform superposition of all pre-images to that image. Now, because we're dealing with this surjective hash function, right? We're mapping 512-bit strings to 256-bit strings. There's going to be, roughly speaking, 2 to the 256 pre-images for that one image, and the private key is basically going to be the uniform superposition of all these things. So far, we've done almost nothing here. There's nothing complicated. Here, this is all like easy quantum stuff. And like one way to think about it is that, okay, we start with all key pairs, and then we just collapse, we kind of randomly sample a specific public key, and then there's like all these private keys that correspond to it. Okay, so let's continue with this diagram. We have a message that we want to sign, and it's a 1-bit message, and we have the private key in purple. Now, what we're going to do here is we're going to do a clever search algorithm. So think of Grover search, for example. It's kind of this quantum algorithm to efficiently search within a search space. And what we have here is that the private key is the search space, right? We have all the pre-images corresponding to one specific image. And really what we want is we want to find one pre-image of those 2 to the 256, which starts with the bit that we want to assign. So if the bit we want to assign is 0, then we basically want a pre-image that starts with 0. And if the bit is 1, we want a pre-image that starts with 1. And basically, the way that we generalize this to larger messages, for example, 256 bits, is that we do this process 256 times, where at the very beginning, I'm going to give you 256 images. You send me a 256-bit message, and then for each of the pre-images, I'm going to, for each of the images, which are the pub keys, I'm going to find a pre-image which matches the corresponding bit. So if your hash function is kind of pre-image resistant, then it's kind of hard to sign, and you have a matching between the signature and the message being signed just by looking at the bits. Okay, just to put this in text instead of visual language, you just start with a suitable hash function h. You build the uniform superposition of all pre-image image pairs. You limit yourself to the space of pre-images of size 512 bits. And then you observe and collapse the so-called second register, which is the qubits on the right-hand side. You get a public key and a private key. The public key is going to be this random image y. It's purely classical. There's nothing quantum there. And then the private key is going to be the superposition of all pre-images to that public key. And then in order to sign a specific bit, you just run this quantum search algorithm, which is, you can think of as being Grover's algorithm. And like the hard bits here, there's kind of two hard bits. One is finding a suitable hash function h, and then the other hard bit is running the quantum search algorithm. The quantum search algorithm is hard because you need a quantum computer, and we don't have those today, and it will probably take decades to get a suitable quantum computer. And the reason why the hash function h is hard is because it's a space which hasn't really been researched much, and we don't really have like good practical candidates yet. Now, it turns out that the property, this suitable property for the hash function that we want is, we want it to be so-called equivocal, which is this idea whereby if you have a uniform superposition of all pre-images to an image, you're able to find a specific pre-image which has a certain property. And it's been proven in a recent paper from 2022 that one-shot signatures are actually equivalent to equivocal hash functions. So if you're given one, you can build the other, and vice versa. And so in a way, the research problem of building one-shot signatures reduces to a design problem of building hash functions, which is pretty cool. And so one of the things I want to do is have a hash function competition. And we've had those in the past. We've had the NIST have hash function competitions. I think that led to SHA-2 and SHA-3. And the Ethereum Foundation even organized a hash function competition for snark-friendly hash functions. And that led to things like Poseidon and Rescue. And maybe someone here in the audience might be interested in helping co-organize a hash function competition. Okay, now you might be asking, okay, is this thing practical? And the answer is no, it's not practical in the short term. But then you can ask, okay, is this even practical in the long term when we do have quantum computers? And there's all sorts of questions you may ask. And it turns out, I think the answer is yes, it's practical, and I kind of want to give you the pitch for why ultimately it will be practical once we have quantum computers. Now, one important aspect that I want to highlight is that the verifier of the signature is purely classical. So the message being signed is classical, the signature is classical. These are normal signatures, bits and bytes. The signature you can think of just being a snark. There's no quantum communication, there's no quantum teleportation. Like the verifier is assumed to be extremely weak. It can just be a smartwatch or a mobile phone or whatever it is. Like all the magic happens on the signer side of things, the prover side of things. Another kind of question you may have is, hold on, like if the private key is a quantum object, aren't like these quantum objects like really, really fragile, right? They decohere extremely fast, and noise kind of just pollutes the private key, and then you just lose the private key. Now, it turns out that there's this really nice trick that you can do where you have a signature chain that I mentioned at the beginning, and you just have lots of dummy rounds of signings, where you just sign on the same state over and over again, which is kind of the trivial state transition function, where you just say, okay, the input must match the output exactly, they must be equal. And the only thing that you're doing is you're basically refreshing the private key just by artificially kind of signing on the last message. And so if your decoherence time is 100 milliseconds or a second or 10 seconds or 100 seconds, whatever it is, you can just make sure to refresh fast enough so that the private key doesn't decohere. And then another kind of question you might have is, okay, if you want to remove the slashing conditions, doesn't this require like every validator on Ethereum to have a quantum computer? And we're talking not just 20 or 30 years to get one quantum computer, but we're maybe talking 40, 50 years to get everyone has a quantum computer. And I guess my answer here is that even one single quantum computer that can do these one-shot signatures would be very, very valuable. And part of the reason is because of these liquid staking tokens, right? In the context, imagine like Google or Microsoft, have this quantum computer that can do the one-shot signatures. Now what can happen is that ETH stakers can now delegate their stake to Google, and Google just can't get the stake slashed. And so in the worst case, what happens is that Google goes offline, but that's fine because now you can just force exit, and because and this exit mechanism, will protect your stake. And then another really cool thing that you can do with one-shot signatures is that once you have one-shot signature scheme, you can make any other signature scheme also one-shot. There's this kind of amazing kind of transfer of one-shotness. And in order to do that, you need obfuscation. So if we have I/O and one-shot signatures, then you can actually use any signature scheme and make it one-shot. There's a compiler that will do that. Okay, last slide, I believe. So in a few weeks, there's going to be a conference dedicated to quantum signatures for blockchains. It's going to be in Edinburgh on January 26th, and there's a website. But if you want an invite, just please get in touch and DM me. I mean, the goal here is to try and get all the experts on quantum signatures in one room and try and move the space forward, and maybe try and think of more blockchain applications and things like that. And that's it, and I think we have time for questions. Thank you. Question there. Nalin, just next, yeah. Just behind you, Nalin. There we go.
What about reorganization of blockchain in terms of one-shot signatures? Will it occur? Which impact it has?
Yeah, so that's kind of the whole magic of blockchain, of one-shot signatures, is that, can we keep the slides actually in case I want to refer back to them? You can't reorg anymore. Like by construction, you have chains that are append only and can grow, right? If you have a reorg, then you're in a position, again, where like half of the validators voted for A, half of the validators voted for B, and like one of the validators voted for both A and B, but we know that's impossible by kind of the laws of physics and cryptography. So reorgs are a thing of the past, and basically the only problem that's being solved with consensus is liveness. I mean, and actually I have a little bit of a mental model here. Like, you can think of consensus as being this very generic like problem-solving tool that can solve many, many problems. It can solve, you know, execution. It can solve data availability. It can solve for safety and reorgs, and it can solve for liveness. And when we started originally, we had blockchains, we had consensus solve for all of these simultaneously. But then we realized that cryptography, one by one, can solve these things that consensus was solving. So for example, execution. Well, we know with SNARKs that you can have ZK EVMs, and you don't need consensus on execution. You can just have this sidecar thing, as Vitalik was saying, that kind of proves that this is the correct execution. Same thing with data availability. Now we have data availability sampling, whereby you don't need consensus to have you know, agreement on data availability. You can just use this kind of clever cryptographic sampling mechanism. And it turns out that reorgs and safety is not something that we need consensus for. It's something that pure cryptography solves. And basically the only thing that's kind of fundamental to consensus is liveness. We just need to be able to gracefully degrade whenever validators go offline. Great question. Any?
Yeah.
Go ahead.
I just wanted to ask.
Can you raise your hand? I can't see you.
How come one-shot signatures are equal to unequivocal hash functions? If you can just explain a bit more.
Right. So when we had a look at the construction, basically we had in a way what I tried to sketch out is how, starting with equivocal hash functions, you can build a one-shot signature. And the key property here is kind of this last step here in the bottom right of the screen. So you have the private key in the middle of the screen in purple, which is a quantum superposition of all pre-images for a specific image. And what the equivocal property tells you is that you're allowed to go search within this quantum superposition for like a special pre-image. And then kind of bring it back to the real world, to the classical world. But the one very important property is that it's impossible to find two pre-images. So it's kind of this very strange thing where we know that there's lots of pre-images. There's 2 to the 256, and you're allowed to kind of selectively pick a few special ones, but you're never allowed to pick two, because if you were allowed to pick two, then now you violated the collision resistance property. So it's kind of this very delicate property to have, where you simultaneously have collision resistance and this weird equivocal thing where you can go search within the space of pre-images. Yeah, and a question here.
Hey, thanks for the talk. I'm really curious about the part of the quantum nature of this. Like, in my understanding with all quantum algorithms and stuff, there's a kind of like probabilistic aspect to it that you need to repeat in order to be convinced of the like output, with Shor's algorithm and stuff like that. Why is it that in this system, like, it seems like you would need to be 100% certain that the one-shot signature is going to work, right? Because if you want to sign the rights over to the next signature, you need the thing the algorithm that allows you to get the bit that you want, it needs to work every single time, or otherwise the chain will be broken, because you need it to match, like, I assume that you need to have another one in parallel so that you can sign over to it, right?
Right.
Why is it that in this system you wouldn't have that problem?
Okay, fantastic question. So there's kind of two answers to this question. Answer number one is that if you work in a probabilistic setting, well, you can just make sure the probability of failure is just low enough. And this is what we do all the time in cryptography, right? If the probability of not being able to sign something is like 2 to the minus 2 to the 56, then we just don't care. And like usually in cryptography, you have perfect completeness, meaning that you can always prove the thing you're trying to prove, or you can always sign the thing you're trying to sign, and you have kind of the statistical safety. Whereas here, potentially you're degrading both the safety and the completeness to this probabilistic thing. But the other answer is that I think in this particular instance, you don't even need that. Like you do have like some algorithms that don't have this problem of probabilities, or at least you might get a different answer depending on every time you run it, but the answer is kind of still a valid answer. So it doesn't break the completeness property. So here in this diagram, you just need one pre-image that has the right property, and you don't really care which one, so long as you have one. And I mean, I'm not an expert in quantum algorithms, but I believe that in this special case, you don't even have this probabilistic problem. But even if you did, it's not an issue. Just run the Grover search sufficiently many iterations so that your probability is small enough. Question here.
Thank you for the talk, very interesting. I understand with one-shot signature, we don't have double voting because essentially each validator gets one vote per epoch.
Yeah.
But how does this prevent surround voting? Can you expand on that?
How does it prevent the surround vote? Right, okay, great question. Yeah, so like these are the specific kind of constraints that you set yourself on the signing. And like basically the condition on so the target being strictly increasing, right? The current target is strictly greater than the previous target, means that you'll never sign two targets the same. That's kind of obvious. And then on the surround vote, basically what you're asking is, you see it, instead of a strictly greater, is greater than or equal. And so you're kind of saying that the source can never go back in time. So let's say you have a source, like basically think of the source as being the justified checkpoint, right? If you're familiar with justified and finalized in Ethereum, we have these two stages to finality, justified, finalized. So imagine that the source is the justified checkpoint, and then you make attempts to finalize with a target, and eventually you finalize. Now, in order to get a surround vote, you need your source to go back in time so that you can surround a pass vote. But because the source can't go back in time, you will never surround because the source is only going forward. It's a bit of a hand-wavy thing, but it turns out the proof is like super simple, just a few lines of proof, and more than happy to share the security proof offline. Yeah, question here, and question here.
Hey, thank you very much for the talk. So I understand that the private key is in superposition,
Yes.
and then when you will run the search algorithm through the superposition of those private keys, will the superposition not collapse, leaving it with the regular state, not quantum? How you can recover from it?
Yeah, I mean, that's the whole point. It's like, when you do the search algorithm, the process of extracting information of that involves observing and destroying the private key. So the private key is the superposition of pre-images, and you want it to destroy itself when you observe it, when you do the search. when you extract the result of the search algorithm. So yeah, you're exactly right. As part of doing the search, you destroy your private key, but this is a feature, not a bug. Question here, and then question there.
Thanks for the talk. Maybe stupid question. You want to reorg also because of social consensus. Is that still possible or not after this is introduced?
Yeah, that's a fantastic question. So kind of two parts to this question. Like one is what I call perfect finality is actually only perfect in the context of consensus, but it's not perfect in the context of governance, right? Because the layer 0 can always fork out the consensus itself. So that's, I guess, answer number one. And then one question you might ask is, does the layer 0, can it still do, hard forks to the consensus? And the answer is yes. And the reason is basically here. Like in the state transition function here, you can just socially fork it out, right? The state transition function itself is not kind of embedded in the physics of things. The only thing that's kind of physically guaranteed is the one-shotness, but the state transition function itself can be changed. So for example, you want to change the definition of the EVM, you want to add a new opcode. That's fine. Now you just change the definition of the EVM, and now you're changing the snark circuit that corresponds to the state transition function. And then when you verify the one-shot signature, you need to verify that the new definition of the state transition function is respected. So yeah, great question. The social layer still has the ability to fork out. I think there's a question over there.
Hi, a question on the construction. So you take like 512 qubits and then you make a hash function. You do the hashing of that. So how does that not violate the no cloning theorem? Because you're still keeping the 512 qubits, but you're also hashing them.
Right, so actually you have more than 512. You have 512 plus 256, which is 768 or something. And what you do is that you load, the way that you run quantum algorithms is that you kind of, you load the qubits, and they kind of all, okay, let me go to the actual thing here. So the way that you get the first step, which is this first purple box, is you load all zeros, and then, so basically all 0 qubits, and then you run them through Hadamard gates, and now you have this uniform superposition. This is like a very standard, like the very first trick that you learn in quantum computing. And then the action that you perform is this observation, where you observe the last 256 bits. So now you're left with a 512 qubit system, and then you feed that through your quantum circuit. And at no point is there cloning. Like there's just no cloning anywhere involved here. There's Hadamard gates, there's loading all the zeros at the beginning, and then there's running through the quantum circuit. But yeah, there's just no cloning involved here. I mean, one thing that you can, quote, clone is all the zeros at the beginning. But the no cloning says that when you have an unknown quantum superposition, you can't do cloning. But it's totally possible to clone all zeros, because that's kind of a known state. I think there was a question over there.
Would the one-shot signatures also allow to get rid of keeping to retain the historical blocks? It's like if we do not need to, like if there aren't forks, then we the current signature it allows to verify the whole chain.
Right. So I actually think that even today there's no need to store blocks. So I have this maybe like slightly controversial opinion that consensus doesn't provide any guarantees on historical storage, right? People often confuse data availability and data storage. Consensus only provides guarantees on data availability, which is kind of this real-time property that data was not withheld. But once the data has been made public, was not withheld, then you have a totally different game. You have what's called an honest minority game. You only need a single person in the world to store the data, and it could be like literally anybody. Consensus is much harder. Consensus, you need honest majority. You need more than half, kind of to be not cheating or malicious. So what I personally believe is that if you're running a consensus node as a validator today on Ethereum, you shouldn't be storing the data blocks. Like your contribution is like minuscule. Like your real contribution as a staker is for data availability, which is this real-time property. Yeah, so that's kind of my answer, I guess. Thank you so much. I think we're out of time. More than happy to answer questions offline. Thank you.